Okay, so as we're kind of sorting that stuff out, main idea that we took from yesterday, okay, and remember our ultimate goal. We want to take these crazy equations that are really complicated, and we want to be able to try and sketch a graph of them like we did with our polynomials. So accurate in some really important aspects, but other than that, just kind of a sketch of what's going on. So over the last couple of days, all we've determined is we can look at the polynomial and know about its end behavior, right? So what's one type of rational function and its end behavior? So like tell me one of the conclusions that we drew from yesterday. Jenna? Good. Okay, so when we have the higher degree in the numerator, the graph has end behavior towards infinity or negative infinity. So no horizontal asymptote, not horizontal ends. Instead, ends that shoot up or shoot down, and we're going to find something to follow to know how fast we rise up or go down. Okay. All right, somebody give me another situation. So that was one of our conclusions. What was another one? You wrote them down yesterday, so they're not that mysterious. Claire? Good. When the denominator has the bigger degree, not only do they go horizontal, but they all specifically go horizontal at 0. They all come back to the x-axis and stay really close to 0. Okay. And what was our third and final one? Yep. When the degrees are equal, you use the least coefficients of the horizontal. Good. So when the degrees are equal, it does get horizontal, but it can be at any different place. And so in order to find what that place is, we use the lead coefficient of the terms that were highest in degree in the numerator and denominator, okay? So are we okay with that from yesterday? So we took the last couple of days to just say, wow, there's these crazy functions. Look at how they behave, kind of ridiculous. We don't know anything about how to create all that ridiculous behavior that's happening in the middle. All we've learned so far is how to know where the ends of the function go. So in order to know what's happening in that function, you guys saw how some of them were split into just like 2 branches. Other ones had 3 branches, okay? One that we looked at in our notes at the beginning didn't have any branches. It was a continuous thing, but it was kind of a weird shape. One was like a line with a hole in it. So how do we figure out these things is what we want to determine. So we want to know how many branches there are. In order to determine that, we have to find the places where it's being cut into different branches. Okay, and so we did talk about this with our reciprocal function. What cut our graph into 2 branches with the reciprocal function? What was on our graph that determined there would be this separation and there would be one branch over here and one over here? The vertical asymptote, right? So vertical asymptotes will be important for us to find because they'll tell us how many branches our graph is cut into and where those separations will be. So those will help us do a good job sketching. Horizontal or oblique asymptotes, we just kind of mentioned oblique a little bit yesterday as the thing we would follow if we weren't horizontal, are important for the ends of the graph. And then we just want to know, like, how do I know? Like, does it turn around? Does it look like a cubic? Like, what's happening in between these asymptotes? And for that, we may want some points, but plugging in points, as we see, can be difficult. So there are a few key points that we can find fairly quickly, our intercepts, like we found with other graphs. We can find our X intercepts and our Y intercepts fairly quickly, so we'll use those points to help us. And besides that, we're just going to kind of like, does it turn out to be positive or negative? Like, should the graph go up here or down here? And we're going to try and go from there to create the sketching, okay? So we're going to look at how to find each of these things, all right? So you guys said vertical asymptotes were the things that cut our graphs into branches. We saw this with our reciprocal function. With our reciprocal function, how did we know where the vertical asymptote went? Or why was there even a vertical asymptote on the graph? What makes these graphs have a vertical asymptote? We put that on the graph because of something that's happening in the algebra. Alex? Good. When the denominator is equal to 0 because the function was undefined, right? So this might be a new situation for us that, like, we've never had a graph where you plug this in and you can't actually do the calculation. It's undefined. We have this new marking for that in a vertical asymptote. So there's some notes here already for you guys if you have the note guide. If you don't have the note guide, you might want to consider printing out this one page or just writing down the important things that we discussed. So a vertical asymptote is where the function is undefined. the graph won't cross this asymptote because no points on the graph exist for that x value. Okay, so we've discussed that before. And so one other thing for them is because it separates the graph, these graphs are discontinuous, right? We've done this before with piecewise. Like some of our piecewise functions were continuous. We could keep our pencil on the paper to draw them. And some were discontinuous, like we drew a branch. We had to jump off that to go to the next branch, etc. So anything that has a vertical asymptote is discontinuous, right? Because it's cutting the graph into the two branches. So sometimes instead of calling them vertical asymptotes, they'll refer to them as discontinuities, as in like the place where the graph is discontinuous. And these ones are called non-removable, and I'll show you in a minute why they're called non-removable compared to the ones that are called removable. Okay? You'll see it kind of algebraically. So vertical asymptotes, another word for them is non-removable discontinuities. The discontinuity part hopefully can connect in your head because it's making the graph discontinuous. Why it's non-removable, we'll look at in a minute. So Alex told us we have the vertical asymptote when the function is undefined. All of these functions are in fraction form, right? That's why they're rational. When are they going to be undefined then? When I'm looking for a vertical asymptote, I know in my head, like let's say this function over here that I have on the board, I know in my head this function is undefined when the denominator is equal to 0, right? Where's the vertical asymptote? -5. So what am I looking at? I'm looking at taking the denominator and finding out when it's equal to 0 because that's going to tell me where my vertical asymptotes are. Is that good with everybody? Okay, so they're right here, like how to find this in short form. We need to understand what it is. And then physically, how do we go find it? We take the denominator and set it equal to 0. Okay, so just set the denominator equal to 0. Okay, and then that will give you x values where you have vertical asymptotes. Now, how many vertical asymptotes could you have? Oh, it depends on the degree of the denominator, right? Okay, let's say the degree of the denominator was like a quintic and it factored and had like 5 factors that could make that denominator equal to 0, then you have 5 vertical asymptotes. Okay, 5 vertical asymptotes splits your graph into like 6 branches. Okay, stuff to fill in on every side of the vertical asymptote. So just hope that you don't get that one to graph, right? A lot of vertical asymptotes. Are we okay with how to find vertical asymptotes? Okay, so what we talked about before, what we spent a lot of time on, horizontal asymptotes and end behavior because there was lots of situations. These are a little more straightforward. Okay, so vertical asymptote, we're setting the denominator equal to 0. Now we're going to look at a couple more things. So we talked about horizontal asymptotes, okay? That's what we've been talking about before, right? So a horizontal asymptote is not where the function is undefined. Yes, sorry, Lee. Yeah. Is not where the function is undefined, okay? What is a horizontal asymptote there to tell you on the graph? Jenna? The end behavior, okay? So could your graph cross a horizontal asymptote? Not at the ends. Normally it just comes up to it and follows it, right? But could it have crossed it somewhere else along the graph? Yeah, okay? It's just there for the ends. Like really a horizontal asymptote, you don't need it in the middle. You really just need like the little dashed lines way out at the ends to show you what's happening, okay? So really differentiate that it's not like you can clump all asymptotes together. They mean different things. Vertical asymptote means undefined. If your function's undefined, clearly you're not going to cross over there. You couldn't get a value, okay? But horizontal asymptote is not that. It's just saying, hey, do all that stuff, and when you're done and you start plugging in these really big numbers and it's done doing all these things, here's what it's going to do. So just come kind of do this, okay? So we already talked about that. So horizontal asymptotes will really help you determine end behavior, okay? So it describes end behavior, and then we're not really going to write a lot about how to find horizontal asymptotes here because we did it in the conclusion charts from yesterday, right? So there's just a note here about seeing the previous chart of conclusions that summarizes it, which is what you guys told me at the beginning. If the degree of the numerator is higher versus if they're the same versus if the degree of the denominator is higher is how you would determine this, okay? And then notice where it says oblique asymptote, which we slightly have mentioned before, it also says end behavior. So these things are describing the same thing, which is why a function cannot have a horizontal asymptote and also an oblique asymptote. Either your ends are horizontal or they're not, okay? So you can't have both. So when our ends are not horizontal, so what's the only time when our rational function will not have horizontal asymptote? What type of rational function will have no horizontal asymptote? Then? Good. So when the numerator is more than the denominator, we said you can't find a horizontal asymptote, and you should go find the oblique asymptote. Okay? So how do we find an oblique asymptote? Okay, so first of all, understanding what it is. It's just like a horizontal asymptote. It's there to follow for end behavior, except for instead of horizontal, it might be slanted. It might be a parabola. You might be following parabola shape at your ends. Okay, could be anything. All right, so how do we find an oblique asymptote? We basically do what the function is saying to do. So remember, a rational function is written like a fraction, which is a division problem. So really, when someone gives you, say, we'll just use the one I have up here on the board, 3x squared plus 2x plus 1 over x plus 5. This would have no horizontal asymptote because the degree of the numerator is higher than the degree of the denominator. And so its ends go towards infinity or negative infinity. And so we want to find what does it follow in that direction. We actually do this division. We're going to go through and do this divided by this. Okay? So in this case, I have choices, right? You can do synthetic division or you can do long division. I'm going to do synthetic division in this instance. Is everybody okay with why I can do synthetic division? If this down here was an x squared and this was a cubed or something like that, I would have to do long division. Everybody understand the difference? Okay. So when I divide this out, in this case, I'd have a negative 5 here, a 3, a 2, and a 1. And I'd go through my synthetic division process. And so basically this tells me the answer to the division problem, remember, is 1 degree less than what we were dividing. We were dividing x squared by x, so it'll just leave x to the first power. So this is my x, this is my constant, and this is my remainder. Okay? So the answer to the division problem is 3x minus 13 plus 66 over x plus 5. And then here's what we do. Remember that end behavior is supposed to be what happens when you plug in like really, really, really big numbers. Remember how we talked about this yesterday, that mathematicians kind of ignore the stuff that doesn't like really contribute a lot to what's happening. So this fraction here, it is part of the answer to the division problem, but it's not really important in what our function is going to do at the ends, because what's going to happen to this fraction if I plug in really, really, really big numbers for x? Shanna? It'll get really close to 0. So it's basically saying like, oh, this is going to get really big because you're plugging in really big numbers, and then you're going to add this like little teeny tiny minuscule thing to it that barely makes a difference. So mathematicians say if you're just trying to find out what happens at the end, this basically becomes 0. This will be your oblique asymptote. Okay? So what that means on the graph is instead of having a horizontal asymptote, which would look like this, and you would expect something to happen where the end of your graph kind of went like that, for an oblique asymptote, you would literally, like you were in Algebra 1, go graph the line y equals 3x minus 13, and it would look something like this. And what that tells you is instead of your function doing all this crazy stuff and then being horizontal, this function's going to do all the crazy stuff and then it's going to like follow that line. And maybe on this side, follow it over here, where its ends are going to go towards negative infinity and towards infinity at the same rate that this line does. Okay? So instead of getting flat ends like this along this horizontal, your ends go towards infinity or negative infinity along this line that you've drawn here. Okay? We'll go through and do some. This is just the general idea. Like, I just want you to leave here right now going, I now understand an oblique asymptote is end behavior when I don't have a horizontal asymptote. I understand I get an oblique asymptote by actually dividing out the function they gave me. I get to ignore the denominator, and we know there's a mathematical reason behind that. We're not just like making math magic. and it would graph something like this, and my ends would follow those ends instead of being horizontal. That's what I want you to know right now. Not exactly how you'd know it came here instead of here. I don't. I'm just giving you an example of what it might look like. Okay? We'll figure all that stuff out later. Is that okay with everybody for oblique asymptote? So not complete understanding of how that looks on a graph. We have to actually do one to understand it. But you understand what it is, that it replaces a horizontal asymptote, how to find it, and like that you would still follow it on the graph like a horizontal, but it's not horizontal. Okay? That kind of idea. Any questions about these asymptotes? Okay, so are we comfortable now understanding how to find all asymptotes? So your homework tonight is going to ask you to find all the asymptotes, the holes, and the intercepts of functions. You're not going to be asked to put anything on a graph. You're just going to be asked to do all the algebraic stuff because that's the stuff that we then want to take and put on the graph that hopefully gives us a good enough picture to like sketch something in. Okay, so we want to be good at the algebra part to get the picture part. So first section is asymptotes. So every time you guys do one of these, I'm just going to have like a list: vertical asymptote, horizontal asymptote, oblique asymptote. Okay? And you're just going to fill in what they are. One of them will always say none. Okay? Which two can you not have at the same time? Good. So when you're answering these questions, you shouldn't have answers for both of those. One of them would be none, and then you'd have an answer for the other, depending on the function and the situation. Okay? Vertical asymptotes, if you have a denominator to set equal to 0, it didn't get canceled out or something like that, then you'll have vertical asymptotes to list. Sometimes you'll have none if they cancel out. Okay? Is this all right with everybody for asymptotes? What's the main difference between vertical asymptotes and horizontal or oblique asymptotes? I see Jenna and Zen, but they both have answered questions for me today. Okay, in your group, take 30 seconds. Tell the people around you like a difference between vertical, because we tend to kind of group all the asymptotes together like they all do the same thing, and they don't. What is a vertical asymptote doing versus what horizontal and oblique asymptotes are doing? Tell the people around you. All right, are we all okay now with what the asymptotes do? Okay. I might ask you that to explain to me why they are different, because it's really important that we don't just assume everything is a line you don't cross. We really have to understand what each thing is there to show us. Okay. All right, the next thing we're going to talk about are holes. So I'm going to give us a function to work with maybe through this whole thing here. whole thing. That was funny. Okay. So first of all, holes are discontinuous pieces of the graph too. Okay, like you guys saw that one graph, like the line with the hole in it at the beginning of our notes on this section. So it's like the whole line exists except for this one point. So you have to like hop over it, like it's not continuous. So they also are called discontinuities at times, but these ones are called removable discontinuities. So holes and vertical asymptotes split your graph apart. Therefore, they are called discontinuities. One of them is called removable and one of them is called non-removable. And the way that you'll be able to see that is in how the equation works. So let's say that somebody gave me an equation, and I'm trying to think of one in my head right now. Give myself a simple one so I can think it up properly. 2 and 1. Okay, so here is a rational function, right? Okay, so oftentimes before we even start, looking at it written in this form, its expanded form, is nice for our horizontal asymptotes or for finding on our oblique asymptotes. If we have to divide, we don't really want it in factored form. We need it written out in standard form. So that would be nice for oblique. In this case, we don't have to find oblique asymptotes, right? We don't have a greater degree in the numerator, so we actually do have a horizontal asymptote. So what would the horizontal asymptote of this function be? Anybody know? Look back at your conclusion chart, right? What are the degrees? What does that mean about finding the horizontal asymptote? Therefore, what would it be? Clear? 1. Okay, right? It would be lead coefficients because it has the same degree. 1 over 1 would just be 1. Okay, so I would expect no oblique asymptote. but a horizontal asymptote at y equals 1. Okay, that's what's happening with my ends. For my vertical asymptote, I would want to set the denominator equal to 0. It's a lot easier if the denominator is in factored form. If it doesn't factor, you're just out of luck and go. But there's also another reason that you should factor first before you just start looking for it. If I factor these two things, so if I rewrite this in factored form, I have x plus 2 times x plus 1 over x plus 2 times x plus 5. So what can happen here? Then? Yeah. These can cancel out, okay? Meaning that this function can be simplified to this. Okay? So here's the difference between removable discontinuity and non-removable discontinuity. Ready? Removable discontinuity, as in it was removed from the equation. See? Okay? Non-removable discontinuity can still make my function undefined, but there's nothing that's going to cancel it out. It's not getting removed. Is that okay with everyone? Okay? So removable literally means it gets canceled out, it gets removed from the equation. So it's really this factor that we cancel out that is going to make a whole. Okay? So the reason that it makes a whole is this. We like to think like, oh, we've canceled this out. That means this is the same thing as this, right? 2/4 is the same thing as 1/2 because we cancel out a factor of 2 and they're equivalent. So we feel like this is the same thing, right? This guy was like this. We canceled out the common factor. They are equivalent. That is true. If I plug 1 into here, I get 2/6. If I plug 1 into here, I'll get the same thing, 2/6 or 1/3. They'll be the same for every value you plug in except for what? -2, okay? Because in this one, what happens when I plug in -2? -2 plus 1 is -1. -2 plus 5 is 3. I get -1/3. What happens when you plug -2 into the way it was before? You get 0/0. What the heck is that? I don't know. Okay, a very undefined thing in our math system. So it's like this is the same thing as this everywhere except for that 1 0 that you canceled out when you factored it. So that's why we have to make it a whole, is because if this is what you were really originally graphing, the graph does look the same as this thing. Except for at this one spot. This one value that you plug in makes a different thing here than it does here. It actually makes an undefined thing. If you graph this, you don't think it's undefined. You just see a pretty little picture with that point filled in. So we would say that our whole is at x equals -2. Okay. Is everybody okay with why the x value of -2 creates a whole? It means it was undefined in the original function. However, it was removed from that and we got a new function. That's the difference between the whole and the vertical asymptote. Okay, so the vertical asymptote makes the denominator equal to 0 even after you have simplified it. Okay? If it would make the denominator equal to 0 originally, but it gets simplified away or removed from the equation, it makes a removable discontinuity or a whole at that x value. Okay, and you can actually get the exact point where the whole exists because remember, plugging -2 in here makes it undefined, but plugging it into the new function, I actually get a point. That is the point that I need to make a whole. That point is -2, comma, what do I get when I plug it into this new thing? We said -1/3, right? Oh, that's cute. So the point -2, -1/3 is going to exist on this graph, and I need to erase it and draw a hole. Is that all right with everybody? Okay? All right, kind of weird, but then like makes sense. The original thing, -2 does not work, okay? You can't plug -2 in here and get -1/3. Is everybody okay with what a whole is? Yeah, check. When you answer where the whole is, you can write either one of these for me, but when you graph it, you're going to have to use the coordinates to put the whole in the right location, which is kind of a bummer, but then also is kind of useful. it's like having a point on the graph that's not actually on the graph. Like if you plot the hole and you just make an open point, you know that your graph should like go through that, but not really go through that. Do you get what I'm saying? Like it would be a point on the graph, but we're just going to skip over it. But it kind of gives you some guidance as to where to draw the picture, okay? Even though it's a hole, all right? Is this okay with how we find holes? So really important at the beginning, we can look at our horizontal like end behavior, but we also should look to factor right at the beginning because we want to know a hole here. We don't want to go do all the work with this more complicated equation when really we could have just taken out the hole and made a simpler equation. All right? So you should take the holes out at the beginning and write down that you have them, but everything else should then be done from here. So like in this function, what would my vertical asymptote or vertical asymptotes be? Where would they be located? Then? -5. Would there be a vertical asymptote at -2? No. Okay? That did make the denominator undefined, but in a different way than the x plus 5 works, right? The x plus 2 factor is creating a removable discontinuity, which is a hole. The x plus 5 factor is creating a non-removable discontinuity, which is a vertical asymptote. So it's important that you look at those factors and see what cancels first. Number 1, so you know if you have a hole. Number 2, so you don't do a bunch of work with a really complicated thing when it could have been simpler. And number 3, you'll get too many vertical asymptotes if you don't look at what cancels first. Is that okay with everyone? All right. All right, and then the last thing is intercepts. We find intercepts the same way we've always found intercepts. It doesn't change, just sometimes the solving gets more complicated or less complicated depending on what's going on, right? So how do we find x intercepts? We found them for a lot of things. Shanna? Good. We plug in 0 for y. Okay? So if I plug in 0 for y, I'm just going to use my same function here. Okay? If I plug in 0 for y, and again, I'm using the more simplified version here. If you guys cancel out that hole, you get to use the more simplified version for everything. Even the horizontal asymptote, you still would have figured out that it's 1 from this equation the same way you figured out it was 1 from this equation. All right? So my advice is factor and cancel at the beginning and just recognize your holes. So a hole kind of becomes for me something I do at the beginning and the end of the process. I want to find it at the beginning, but then I don't use it again until I'm graphing after I'm done with getting all this other stuff. Okay? So if I set the y equal to 0, how do we solve rational functions? How do we cancel out fractions so we don't have x's all in denominators and all this kind of stuff? Yeah, Brandon? So we do multiply, specifically though by the LCD, right? That's what we were looking to do before. So in this equation, there's only one fraction, this one. Its denominator is x plus 5, so that's the entire least common denominator. So I want to multiply both sides of this equation by x plus 5. When x plus 5 multiplies the 0 that's on the left side, we're going to get 0. And then when x plus 5 multiplies the fraction that's on the right side, it's going to cancel out, and we're going to get x plus 1. And so we're going to get -1, 0. Can anyone shorten this process up? I'm not big on shortcuts, but once you guys do this enough, it's kind of like our quadratic formula and stuff like that. Like how I said, mathematicians probably got sick of doing this over and over again, so they just made a formula that does it. Yeah, Anila? Yeah, set the numerator equal to 0. Do you guys see why that's going to work every time? It's not really a shortcut or a trick, but every time, if you're putting 0 in for y and you multiply by the denominator, and we don't have extra things over here, right? Our rational functions are just one big fraction. So every time this is going to be the same as this and cancel it out, and this times 0 will always be 0. You will always be left with the numerator equal to 0. That's what's going to make your x intercepts, okay? So kind of a shortcut. Not really, you don't have to use it, but makes it a little bit simpler. Okay. Any questions on that x intercept? How many x intercepts could you have? Yeah, lots. Okay, it just depends on how many factors there are in that numerator, stuff like that. Okay, because our function, remember, split into branches. It can come back and cross the x-axis as many times as it wants. Okay? And then for y-intercept, we set x equal to 0. So in this case, you would just be plugging in 0 for x and following the correct order of operations, get your numerator value and your denominator value, and in this case we get 1/5. How many y-intercepts can there be in one of these functions? Decide in your group. Take 30 seconds. How many y-intercepts can there be? All right, what do we think? I think Alex is right. Alex, tell everybody. 1. There can only be one y-intercept maximum. We are studying functions. Remember how I said you can't be horizontal and be oblique at the same time because you would violate the function rule? Since we're studying something specifically that is a function, it has to pass the vertical line test, which means when I plug in an x, I can only get one y that goes with it. So like when I plug in 0 for x, there should only be one y value that lines up with that. However, X intercepts are looking at different x values later. They can come out to still equal y and still pass the function test. It wouldn't be 1-to-1, okay, if it had multiple x intercepts, but it would still be a function, okay? So there can be multiple x intercepts, but only one y intercept. There can be multiple vertical asymptotes, splitting our graph into different branches, but only one kind of end behavior, all because we're studying functions that have like the x should only result in one y, so it should pass the vertical line test. We didn't say they're all 1-to-1, okay, so it doesn't have to pass the horizontal line test. Does everybody feel like they could take an equation now and figure out all of these things about it? Not graph it yet, okay? We're going to work on that. We'll do one today, and then we'll work on that on Monday, essentially, okay? But do we feel like we can find everything out here? Okay, so let's try one graphing problem, just to wrap our head around why we want to know all of this stuff and to kind of review this stuff, and then our emphasis Monday will be the graphing. So let's see what we got on here. All right. Let's start with B, I think. B. Yeah. We're actually going to do this, okay? Part B. All right, so the first thing we want to do, we can't just like sit down and start graphing. Like we have no idea. Look at it, okay? But what we want to do is make a list of all of these different characteristics that are going to help us understand pieces of the graph. So for our asymptotes, there's 3 different things we're looking at: vertical, horizontal, and oblique, okay? So I'm using these abbreviations for those. If you don't know what it means, ever ask. You can use the same on your paper, okay? We also know that we want to factor first and look to see if there's any holes. And that then we want to be able to find x-intercepts and y-intercepts to give us a couple of points that we can quickly figure out if they exist on this graph. So in this function, the numerator has been factored for you. That can be a blessing or a curse. We definitely need to look at it factored to see if anything cancels out, to see if there's that whole aspect here happening. However, if we eventually had to go divide to find an oblique asymptote, we want to multiply it back out, so we had it in standard form. So there's just kind of pros and cons to each form. But right now, we're just going to look to see if anything cancels before we continue so that we don't do extra work with things that we didn't have to work on. And so we want to know if this factors down here. I think it should. I get like 6, right? And 1. Okay, so 2x plus 1 and x minus 3. All right, so there's everything. Does anything cancel out? No. So what does that tell us about the characteristics of our graph? There's no holes. There's no removable discontinuities, okay? So none. Then we're going to look at asymptotes. Then we'll get our intercepts. So asymptotes, vertical asymptotes. Do we have any? So do we have stuff in the denominator that could create a 0 in the denominator? Yes. Okay. How many different options are there for creating 0 in the denominator? 2. Okay. And they are occurring at which value? So if I set 2x plus 1 equal to 0, I would get negative 1/2. If I set x minus 3 equal to 0, I'm going to get 3. Okay, so 2 vertical asymptotes. So how many branches will this graph have? 3. So when you draw 2 lines, like say you had a sheet of paper and you drew 2 lines down it, you just split the paper into 3 sections, right? Okay. All right, horizontal and oblique asymptote. These are the ends, right? What's happening at the ends? One of them is going to be none, because either we're horizontal or we're not. Does this function have a horizontal asymptote? And the answer is yes, as long as the degree of the numerator is not higher than the denominator, right? So the degree of the numerator, if I multiplied it out, would be what degree? 2. The denominator also is of degree 2. So we will have a horizontal asymptote, so we don't have to do that division. No oblique asymptote. Clearly, when you have an oblique asymptote, like the problem is going to be more work, and generally it's going to be harder. We tend to like it when they end horizontal and see the picture better, and when they end oblique, it's a little harder for us to understand what to do with it. So we do have a horizontal asymptote, and what will that horizontal asymptote be? So 0 is if the degree of the denominator is greater, which it might look greater in this format, but remember, if we multiplied out the numerator, it's actually also going to have an x squared in it, which means the degree of the numerator and denominator in this case is the same. Jesus? Good. So we're going to use those lead coefficients that would be there if we multiplied out. So the horizontal asymptote would be at 3/2. And so here's generally what we mark on the graph. So we're going to go through and mark our vertical asymptotes to split our graph into the branches. So I'm going to mark one at 3. And one at -0.5. So remember, those are barriers that I cannot cross. Those are undefined sections, 3 different sections of graphing, compared to this horizontal asymptote, which is really just there to tell me about the ends. So we generally mark the horizontal asymptote all the way across, so it's at 1.5. So we mark it like this. But remember, you can actually like erase it in here if you're not good at understanding it, can't cross it. It can totally cross this. This means nothing in here. It means something out here at the ends, but I need to follow that. Okay? There's no holes, so there's nothing else for me to mark right now. And then I'm just going to have an x-intercept, y-intercept. Hopefully, they're helpful. Maybe. Okay? We'll kind of figure out what we're supposed to do. So I'm going to go find x-intercept and y-intercept. So remember, for x-intercept, we said basically we're setting the numerator equal to 0, okay? We're really setting y equal to 0. If we set y equal to 0, we multiply by the denominator, it cancels these out and still leaves 0 on the other side. So we can just set the numerator equal to 0 if we see that. If we don't see that, set y equal to 0 and go through those steps, and after one step, you'll get right where we are. So for our x-intercept, do the work over here since I have space right now, we're going to set 3x times x minus 1 equal to 0. And that means the 3x could equal 0 or the x minus 1. So that actually gives us 2 x-intercepts, one at 0 and one at 1. So I'll mark these in green. So the x-intercepts are at 0, 0 and 1, 0. And then y-intercepts, some of you might already know because based on one of our x-intercepts, there's not a lot of choices for the y-intercept. But if you plug 0 in for x, you can calculate it. If we plug 0 in for x in the numerator, we would get 0 because of that right there, right? That 0 times whatever is here is 0. And then in the denominator, we get minus 3, but 0 divided by any other number is still just 0. So our y-intercept also ends up being at 0, 0. So here's as much information as we have. All right, so here's what we tend to do. It's kind of like, and I don't think you guys liked this, so I'm not sure you're going to like it. Remember with our quadratic inequalities when we were solving them and we made the little number line and we just plugged stuff in to figure out if it was positive or negative so we knew whether it was like above or below? That's kind of the easiest way to do this because you essentially have like, what the heck is happening over here? No idea, right? Okay, so I want to know what's happening on this side of negative 1/2. So I'm kind of thinking of negative 1/2 as a barrier, and I want to know what happens when I plug in a number smaller than negative 1/2. So let's say I plug in like negative 10. Okay, so basically, I can plug it into each of these factors. I think it's easier to plug it. You can like literally go plug in negative 10 and do some intense calculations. I'm just going to look at negatives and positives because that's enough information for us. When I plug in negative 10 here, 3x would be negative. When I plug in negative 10 to this factor, negative 10 minus 1 would be negative. When I plug in negative 10 here, it will be negative. And when I plug in negative 10 here, it will be negative. All of that work will end up creating what? A positive, right? Okay, so all I know is that on this side, it's positive. Now, let me show you what that means on the graph. You guys don't draw this, but it kind of gives you a technique if you want to later. That means whatever you graph over here must be above the axis. That's what that means. That's the interpretation of this, okay? So, this is going to be a little bit much maybe for you guys, but we're going to work. Remember, we're going to work more on this on Monday. We're not trying to master this topic right now. We're trying to like preview it. I know my end has to follow this. I know I don't hit the x-axis over here or go below it. And I know that when I get closer or closer to a vertical asymptote, that it either goes up towards infinity or down towards negative infinity, okay, as the separator. So here, as I get closer and closer to this asymptote, will I be going up towards infinity or down towards negative infinity? Up. I have to go up. Look where the points have to be plotted. Right? It said positives. So I know that the part of my graph that comes here has to follow that there. Okay? Now, it could cross this. I don't know exactly what's happening, but I do know that over here at the end, it's supposed to end horizontal to this, right? So you could technically come down here. You cannot come all the way down to the x-axis. There is no X intercept, and you can't go below it because there's no negative values. You could technically like come in. Who knows? Maybe it goes like this for a while. I don't know. Okay? However, I know that it has to end following this. So kind of the simplest way for me to draw it is something like this. Sorry, that didn't work out so well, but you get the idea. So I follow the asymptotes. This is the sketching part, right? I sketched something where every time you plug in an x, you would get a positive y. It follows the right end behavior and goes up to this asymptote. Then do I know if I'm supposed to be up here or down here on the other side of the asymptote? I don't know. It completely separates my graph, so my graph can go start in a new spot. So I have to check the other side of negative 1/2, but I have to be careful because I do touch right here, which means I can, let's say it was up here, I can cross through this or turn around at this, right? An X-intercept is a place where you could change from being above the x-axis to being below. So not only do I have to pick something bigger than negative 1/2, but it specifically has to be between negative 1/2 and 0 because it could change after 0. So I'm basically taking every place it could change to the next place it could change, and I have to test numbers in that spot. Okay? So let's say we plugged in like negative 0.1. Okay? Negative 0.1 would make that negative. It would make that negative. It would make that negative. However, it would make this positive. Okay? And how's that overall going to work out? A negative times negative in the numerator, positive times negative in the denominator, negative. Okay? So here, the results are negative, meaning, again, you guys don't have to draw this yellow stuff. I'm just trying to get you to understand what these positives and negatives mean. Any x you plug in between negative 1/2 and 0 has to produce y values down here. Okay? So all that tells me is that on this side of this vertical asymptote, am I going up towards infinity or down towards negative infinity? Down towards negative infinity, right? And then I know I hit this point. This is where the X and Y intercepts are handy. That's like an actual point on the graph. And then two things can happen. Do I go through it, or do I turn around and come back here? I don't know. So I have to test what happens after 0. But I can't just pick any number after 0. It has to be between 0 and 1, because 1 is another spot that it could change what it's doing again. So then I would go and I would plug in 1. Okay? So we're going to finish this on Monday. We'll go through the whole thing again. But you guys get the general idea of how we're using these things. So the hard part for us so this is what you should be able to do right now. Okay? On Monday, our goal is to get good at this. So for some of you, this is enough. You're like, I understand. I can go. I can sketch graphs. Okay? For others of us, we're like, this is super weird. Okay? I really have to wrap my mind around what's happening. That's what the little yellow shading is for. I know it's weird, but it at least tells us, like, I have to draw here, and it kind of helps us figure it out. And so we're going to try to master that idea on Monday. Okay? The idea of taking this list of information and putting it over here correctly to get a sketch. Do you guys understand why we're sketching now and not graphing exactly? Who wants to plug in like millions and millions of points? Not me. Okay? All right?